Hey everybody, welcome back to Geometry. This is Mrs. Gunn, and today we are going to be talking about Chapter 2.4, Curves and Circles. So get your guided notes out so you can work through these with me, or go print it off of Ngrade if you need to, and then come back and let's get started together. Okay, so we are going to define a triangle. Now you guys all know what a triangle is, but there is actually a definition in geometry. The union of segments that connect three non-collinear points. A triangle is designated by the symbol triangle and followed by the three non-collinear points. Okay, so here's a diagram. There's a triangle, and I'm going to name the 3 points that the sides of the triangle are connecting. Okay, so let's see. This is a side, and this is a side, and this is a side. Okay, that we call it a vertex. Plural is vertices. So A is a vertex also, and B is a vertex. And the angles are in here. Angle A, angle B, and angle C. Okay, so I can say my sides are AC, AB, and BC. And I can name the vertices are A, B, and C. And I can say that my angles, I can call them angle A. You're allowed to name an angle with one letter if it's obvious that there's no other angle that could be called that letter. Angle B or angle C, or I can name angles with 3 letters. So angle A, as long as we put the vertex letter in the middle, I could call angle A angle BAC. That's another name for the same angle. Angle B I could call angle ABC. And angle C I could call angle BCA. Any of those are appropriate for naming. Okay? And we name the triangle A, B, C. Or we could name it triangle CBA, or we could name it triangle BCA. It doesn't matter as long as you pick one vertex and move around it in order from vertex to vertex and then name it that way. So naming a triangle, the sides are opposite and the angles are opposite. So if I say triangle, I'm looking for my pen, triangle ABC, then I could say that segment AC is opposite angle B. And angle A is opposite side BC. So when we're talking about opposite, we're talking about across from. So this angle, angle B, is opposite or across from side AC. Okay? And I could say angle A is opposite or across from side BC. And angle C is opposite or across from side AB, and so forth. A curve is a continuous set of points. Okay? So any kind of doodle, that's a curve. This is a curve. This is a curve. This is a curve. Okay? Any set of continuous points, as long as you draw without picking up your pencil, Even if it crisscrosses, has jagged corners, as long as you draw without picking up your pencil, it's a curve. Okay? So, draw without picking up. Now there are different kinds of curves. A closed curve is a curve that begins and ends at the same point. There's a closed curve. There's a closed curve. There's a closed curve. Okay? And even they can backtrack and they can crisscross. As long as I begin and end at the same point, it's a closed curve. A simple curve is a curve, that should say curve, not cure, curve that does not intersect itself unless the starting point and the ending point coincide. So a simple curve would be that, or that, or that, okay? It does not intersect itself unless the starting point and ending point collide. I could have drawn that. That's also a simple curve. It's a closed curve as well, okay? You never cross your path. A simple closed curve. A simple closed curve is also a closed curve, but it doesn't crisscross itself. So that's a simple closed curve. So is that, okay? It doesn't crisscross itself. A circle. A circle is the set of all points that are a given distance from a given point in a given plane. Okay? So, let's see how well I can do a draw in a circle here. Let's move that. There we go. So here's a circle, okay? The center point is right about there. So every single point that's on this circle is the same distance from the center point. And all of this exists in some plane. Maybe we could call it plane M, okay? So that would be an example of a circle. Now, the next thing we have is the center of the circle, okay? So the center of the circle is obviously this point in the center, and it always has a name. A lot of times it's point P, but it doesn't have to be, okay? And we name the circle by that point. So we would call this circle P, and your abbreviation, your notation, looks like this. A dot with a circle around it and the letter P. That means circle P. Okay, the next thing we want to talk about on a circle is a radius. A radius is a segment that connects a point on the circle with the center. So that would be a radius. Okay? We could draw a lot of different radii. Plural is radii. Okay? I could draw, think about how many ways could you cut a pie. There's one. Whoops. There's one. Okay, so you get the idea. All of those are radii. Each one is a radius. Okay, and so let's see. Let's name, there's P. Let's call that Q. So we could say that segment PQ is a radius of circle P. Just like that. Okay. The next thing on our list here for a definition is called the chord of a circle. So let me throw point P back on here because this is circle P. A chord is a line that goes, it's a segment having both endpoints on the circle. So it's a line that goes from one place on the circle to another place on the circle. That should touch. Okay? A chord can go through the center. There's a special chord that goes through the center we're going to talk about in just a second. There's a chord. I could draw another chord over here. As long as both of the endpoints are on the circle, it's a chord. Okay? A diameter is a chord that passes through the center of the circle. So there can be only one way to draw a diameter. It has to pass through the center and have both endpoints on the circle. Now, that one kind of overshot a little bit. You can draw diameters any direction, but they have to pass through the center and end on the circle. That's a diameter. Let's see. That's a diameter. Every time you slice a pizza, you're cutting a diameter if you're cutting through the center. Okay, an arc is a curve that is a subset of a circle. So here's circle P again, and let's put points A and B on here. Okay, this part of the circle that goes around the circle from A to B, we call this arc AB, and you write it like this. AB with an arc symbol over it. Arc AB. Let's throw another letter on here. Let's make this C. This part of the circle going around this way would be called arc BC. Like that. Okay? What do you think this one would be called? I'm guessing that you said arc CA, or you could have said arc AC. Doesn't matter which direction you name it. Same thing for these others. It doesn't matter which direction you name it. Just name the two endpoints of the arc. All right, so let's do some examples. You have a diagram that looks kind of like this on your guided notes. Name the circle. Well, you should have said circle Q, because we name it by its center point. Name a radius. Well, you could name a few different radii. You could say segment QM, or you could have said segment QP, or you could have said segment QO, or you could have reversed the letters. You could have said segment MQ, segment PQ, segment OQ. Those would have been all radii. Name a diameter. There's only one diameter drawn, segment MP, or you could say segment PM. Name the center. Q, point Q. Name a chord. Well, there are lots of chords we could name. We could name LN. We could name MP, even though that's a special chord called a diameter. We could name QO. Okay. QO, is that a chord? No, that's not a chord. A chord, what's the rule for a chord? A chord has to go from one end of the circle to the other end of the circle. Both ends have to be on the circle. So there are only two chords we can draw there. Let's name an arc. Lots of arcs we could write. We could say arc LM, or we could say MN, arc MN, or we could say arc NO, or we could say arc LO. Arc LO would go from L all the way around to O, like that. So there are lots of arcs we could name. Okay, some more terminology. The interior of a circle and the exterior of a circle. This is pretty simple. Let's draw a circle. Guess where the interior is. And guess where the exterior is. If we draw a plane, the circle is always going to be in a plane. The exterior of the circle is going to be out here. It's the complement of all of the points in the plane that lie outside the circle. Okay? So our definitions for the interior: the set of all planar points whose distance from the center of the circle is less than the length of a radius. If you think about where's your center point, roughly right here, every single point that is inside the interior of this circle is going to be a shorter distance away than a radius, because a radius is how long? A radius is going to be this long. So every point that is in the interior of the circle has to be, let me get it on the center. There we go. Every point that is on or in the interior of the circle has to be a shorter distance away than the length of the radius. And to go along with that, the exterior of the circle, any point that's longer away from the center than the radius would be in the exterior. Because we have to make everything complicated with a definition, right? So, pretty easy, pretty self-explanatory, really. Theorem 2.1, the Jordan curve theorem. Any simple closed curve divides a plane into three disjoint sets: the curve itself, its interior, and its exterior. We talked about something like this with lines. We talked about how a line divides a plane into three sets. There was the half plane over here, a half plane over here, and the line itself made three sets. Okay, similar idea. Here's a plane. Here's a curve in the plane. Okay, so there are three distinct sets of points. There is the interior of the curve. All of these points are one set. The exterior of the curve would be everything out here. Pardon me not being so pretty with the coloring. Okay, and the third set is the set of points that are actually on the curve itself. Okay, three different sets of points. Okay, so here's another term to throw at you: region. A region is the union of a simple closed curve and its interior. The curve is the boundary of the region. So here's a plane, and whoops, here is a simple closed curve. Okay, So just like we said, it makes 3 disjoint sets. Well, if we were to consider the interior plus the actual points on the curve itself, those two regions together, those two sets of points together make a region, okay? The interior of the curve and its points that are actually on the curve. And this curve is a boundary. Okay, so here are a couple of examples from your homework. In numbers 18 through 24, they have this first diagram here, and let's just do number 20 for example. Number 20 says, what is the intersection of triangle ABC and triangle ADE? So where is triangle ABC? Triangle ABC is just the points on these 3 line segments, not including what's in the middle, okay? And triangle ADE is the points on the 3 line segments that make the sides, not including the interior. So what would the intersection of the two be? Where do they share in common? Point A. Your book has it like this because it's written in set notation, but if you put point A like that, that's fine. Now number 27 is part of a group that has a diagram that looks something like this, okay? And they want to know true or false, with S being the plane that's shaded, okay? The shape that is shaded, all right? We're not talking about planes here, we're talking about the shape, okay? So the green part here is everything in the interior of A, H, F, G, including, because we're told it's a region, all of the points on the sides. Okay, because remember a region was the sides plus all the interior points. Okay? And they want to know, and they're calling that S. All the green part is S. They want to know, true or false, the intersection of S with BGED is BGFC. So take a second and look at that and see what you think. Where is BGED? BGED, let me use this magenta color. BGED is just the sides that make this rectangle. Just the points on the sides. It does not include anything in the interior. Okay? Okay? That's BGED. They want to know, is the intersection of these two shapes, everything green and just what's pink that turned black when I put it over the green, is the intersection of those the shape BGFC? Is that true or is that false? That is false. What really is the intersection of those two shapes? The only things that are the intersection are where the green and the magenta overlapped and turned black. Those are the intersection, not the whole box BGFC. See here how CF didn't turn black? In order for this to be true, CF would have needed to turn black also. They would have needed to have an overlap. But CF is not part of BGED. Okay, so that's false. That one's tricky. Okay, so I think that's everything you need to do the homework. Give it a shot. Let me know if you have questions. Some of these are challenging, and we'll go over them together. See you soon. Bye-bye.